So the outline is as shown here. Firstly, I would like to take this opportunity to introduce our company, Vitals PLM, on who we are and what we do. I'm not going to spend much time here. And then we move on to a brief introduction to STAR-CCM as a CFD code, as well as the integral part of complete PLM solution offering from Siemens Digital Enterprise. Finally, we spend much time on the topic of the day, the Aeroacoustics analysis using CFD. And for that matter, we use STAR-CCM and we'll see what are the different modeling approaches within the STAR-CCM for performing the aeroacoustic analysis. And finally, we will wrap up with a coupling option to perform Aero-Vibro-acoustics, and then followed by a Q&A. Vitals PLM as a company have a multiple industry experience, namely oil and gas, machinery and equipment, petrochemical, process, nuclear, aerospace, etc. And we are based out of Houston, Texas. And Vitals PLM is a solution partner to Siemens PLM products for STAR-CCM, FEMAP, NX Nastron, AMSIM, BDS Battery Design Studio, PITS, which is the multi-objective design optimization software. And we are a team consisting of mostly PhDs and masters with a background in solid mechanics, fluid mechanics, materials and corrosion, and optimization and data analytics. And Vitals PLM provide engineering consultancy services, and also we cater our services to the needs of automation and customization in the organizations. And when it comes to CFD, Vitals PLM has capabilities with its rich consulting experience by delivering some of the challenging projects successfully for oil and gas and process industries. And these projects involve physics like erosion, corrosion, fluid stress interaction, mixing and separation, acoustic source modeling. On the marine and offshore industry side, Vitals PLM has experience with jumper VAV, floating systems, ship dynamics, riser and pipeline VAV, which is vortex induced vibrations. A brief introduction to SimCenter STAR-CCM. SimCenter STAR-CCM is a multi-physics solution for CFD engineers. With a single integrated user interface, it helps users to cover complete application scope with a broad range of validated models for various disciplines. And these physics are not just limited to CFD, but also extends to high-end topics like electromagnetics, multiphase flows, particle dynamics, reacting flows, electrochemistry, aeroacoustics, which is the topic of the day, computational rheology, and computational solid mechanics. Here we can see some cool animations in front of us. To start with the first one, where we see it's a multiphase application where we see some gases coming from the bottom and interacting with the free surface of heavy fluid. And the second example we see from the automotive industry, where we see a high performance car and the flow field around it is represented by the vertical structures around it. And we see an example from the turbo machinery industry, where we see rotor and stator interactions. Another example from the automotive is where we see it's a water management example, where we see the wiper, how it is wiping out the rainwater. And here the motion is modeled by a technology called Vortex. Another example for the motion where we see from the mining industry, where the mining material is modeled as a particle, DEM particle, discrete element method particle, and also it involves dynamic fluid body interactions for modeling the motion. Another example we see again from the automotive, where we see the flow inside expanding and collapsing IC engine, internal combustion engine, where we see the mesh is expanding and collapsing within the cylinder while the pistons are moving in the suction manifold and exhaust manifold. Another good example from the marine industry, where we see two ships are interacting with each other by the connected catenaries. Again, here the ships are modeled as the DFBA bodies, which stands for dynamic fluid body interaction. And the next example we see here is again an automotive example from the after treatment example, where we see the flow which is going through the static vanes and interacting with the static vanes. And finally, we see an example from the electric machines where the rotor is rotating against the stator, and not so along with the fluid dynamics. So the electric equations, electric field equations are also solved. When I say SIM Center STAR-CCM Plus, the SIM Center is a broader portfolio in which the SIM Center STAR-CCM Plus is included, and this platform combines the best-in-class CA simulations with the system simulation and testing solutions, and also with the design exploration and analytics. All these solutions work together under one umbrella to help engineers to innovate and come up with the products faster to the market with a greater confidence. Here we see the industries and some of the industries and some of the applications in these industries where the aeroacoustic analysis is needed and is important. To start with the marine industry, so the propeller noise is important, and the aeroacoustic analysis needed to predict the noise generated by the propeller. And there is a cavitation noise and also non-cavitation noise, which are important analysis in the marine industry. And there is hull and propeller rudder interactions. When these components interact with each other, there's noise being generated, and then aeroacoustic analysis is needed for predicting these noise sources. In the automotive, we have a big list to start with the wing mirror or the side mirror noise and sunroof noise, which is mainly because of the buffeting phenomena in the sunroof. And we have HVAC systems. And these HVAC systems contain a lot of ducts, and the internal rushing flow would become a source for noise and sound. And turbochargers, which are rotating components in the automotive industry, they also have a lot of noise issues. And cooling fans in the air conditioning systems, again, they are also have a lot of noise issues. Exhaust systems, the mufflers in the exhaust system line, they also have typical sound sources which are need to be addressed. At interior transmission, like at the driver ear, for the comfort of the passenger and the driver, there's a need to build quiet cars, and the sound which is experienced by the occupants inside the interior of the cabin, that's equally important, and where the noise need to be uh, accurately addressed. And in the electronic cooling industry, again, the fan noise is something which need to be addressed. And air conditioning systems also have ducts like HVAC systems in automotive, and there's a lot of noise sources need to be addressed. In the power generation, there are a lot of piping systems, ducts, and cavities. And in the cavities, we can observe a phenomena called resonance, where two frequencies match each other, and then as a result of that, we see the sound levels are magnified because of this resonance phenomenon. And the power generation industry also have rotating components like compressors, turbine, combustors. All these rotating machinery have significant noise sources, and which are need to be addressed. In the building environment, again, there is a lot of HVAC ducting, and internal rushing flow could be a source of sound. And building environment also have the fans, a lot of fans, and then noise is an important issue there. Finally, in the aerospace industry, the high-lift devices, they also have sources of sound, and the landing gear. In the landing, during the landing, when the landing gear opens up, the high-speed turbulent flow around the landing gear became the source for the sound. ECS, electronic control systems, they also have some sort of noise issues. A jet and turbo noise, the the flow which is coming out of the jet engines would have a high high turbulent flow, and then that become a source for the noise. Propellers and cavities are equally important in the aerospace industry for aeroacoustic analysis. So in the previous slide, we have seen HVAC duct is there in the couple of industries. Here we see a 90-degree elbow of the HVAC duct, where because of the 90-degree elbow, we see there is a strong flow separation. As a result of that, there's a lot of turbulence which is injected into the plenum, which is connected um, to the this 90-degree elbow duct. And this plenum we can think of as uh, the vehicle cabin space, where this highly turbulent flow has been injected, and that become a source for the sound. And the second example we see here is the sunroof buffeting, where the flow is represented by the three-dimensional vertical structures colored by pressure. What we see here is the flow which is separated from the leading edge of the aperture is interacting with the trailing edge of the aperture, and resulting in the highly unsteady pressures on the surface of the trailing edge of the aperture. And as a result of that, the sound is produced, and part of the sound is going inside to the cabin and creating annoyance to the occupants inside the cabin. And the part of the flow is going out of the aperture and going out into the vicinity of the vehicle. The third example we see here is the compressor. Uh, Here we see the compressor is rotating in the high RPM of the orders of 20,000. And as a result of that, we see highly localized pressure fluctuations on the rotating surfaces. And this that become a source for the sound. Uh, and again, we have discussed the landing gear in the aerospace industry. Here we can see highly turbulent flow around the landing gear in its opening configuration, and that this highly turbulent flow would become a source for the sound. And here we see it's interesting here. See, it is called singing of the pipe network, because this piping network, we can see there is a rhythmic flow fluctuations inside the pipe, and there is a frequency associated with this pulsation. And when the frequency of the pulsation of the flow is matched with the natural frequency of the structure of the pipe, and at that frequency we see a magnification of the sound pressure levels. So that's what this is called singing of pipe network. And finally, we have a hydroacoustic problem from the marine industry, where we see the cavitation noise as a result of the vapor bubbles collapsing uh, locally inside the equipment, causing a lot of noise being produced. So after having a look at the applications and industries, let's get into the basics of acoustics and as well as the aeroacoustics. So what is sound? So the classical definition for the sound is small molecular vibrations in the medium interest. Here we see the example where we see there's a vibrating plate which is vibrating back and forth. And as a result of that, the vicinity of the air molecules are undergoing a phenomenon called compression and rarefaction, and which results into the longitudinal wave propagation. And also the sound is called a mechanical wave because of this phenomena of compression and rarefaction. The same thing can be visualized more effectively by some animation in the next slide. Here, this animation is taken from the ISVR, which stands for Institute of Sound and Vibration Research from UK. Compared to the previous slide of vibrating pipe, here we have a reciprocating piston, which we can think of a vibrating pipe moving back and forth. And as a result of this reciprocating motion back and forth, what we see here is the molecules adjacent to the reciprocating piston undergoing rarefaction, compression and rarefaction, and which can be defined as a sound classically in the classical acoustics. But when it comes to in the presence of flow, the sound, the way the sound is pursued is totally different, and especially in the presence of the turbulent flow, it is the definition is quite ambiguous because the turbulence creates pressure fluctuations, and it's difficult to separate the fluctuations created by the sound propagation from the pressure fluctuations created by turbulence. And also, the non-homogeneous flows will alter the path of sound propagation. Here we see an example. There's a flow on a cavity of long aspect ratio. The flow is separating from the leading edge of the opening, the cavity opening, and creating a highly unstable oscillating shear layer, and which is interacting with the trailing edge of the opening, and creating a lot of unsteadiness on the surface pressures there, and which become the source of sound. And the streaks we see on the top of the cavity are the signatures of the sound propagation. So to simplify the terms, sound is what propagates with the speed of sound in the presence of the flow, and which is very different from what we have seen as a definition of sound in the classical acoustics. It's good to have an understanding of various quantities in the aeroacoustic analysis. Here we have speed of sound, uh, which is denoted by C, and sometimes some people call it as A infinitive. And we have a fluctuating pressure as a function of space and time, and velocity as a function of space and time, and frequency, which is measured in hertz cycles per second, and angular frequency, which is 2 pi times of the frequency, and the wavelength is the ratio between the speed of sound divided by the frequency, and the wave number, which is called the spatial frequency, is defined as the ratio between the angular frequency to the speed of sound, and opposite to uh, the frequency is the wave period, and we have wave amplitude. So another important uh, term in aeroacoustic analysis is the root mean square of the pressure. To understand this RMS pressure, here we have an example of instantaneous pressure time history for 5 seconds, and this pressure is fluctuating around atmospheric pressure, which is at 10132 Pascal, and by definition and by the name it implies, root mean square pressure is nothing but is this square is the square root operated on the time average of the squares of the fluctuating pressure, which is given by the difference between the instantaneous pressure and the atmospheric pressure. And here you can see the mathematically that is represented as a square root of 1 by t to the integration of the squared fluctuating pressures. And this is important because here for this example, the RMS pressure calculated for a given time of 5 seconds is 10 Pascal. Though the number looks smaller, but in terms of the sound it is going to produce is significant. Once we understand the RMS pressure, we can use it to define the sound pressure level. And the sound pressure level is related to the energy carried by the sound wave. Oftentimes it is denoted as LP, and mathematically it is given as 20 times to the base 10 to the log of the ratio between the RMS pressure to the reference pressure. And here the reference pressure is 2 times the 10 to the power minus 5 Pascal, which is called as the threshold of the hearing. Uh, to put it in an example, just imagine in a room of standstill air, if there is a mosquito 3 meters away from you and flapping its tiny wings, and the fluctuations it's going to create in the standstill air would be the order of the reference pressure, which is 2 times the 10 to the power minus 5. And that's the least possible sound we can hear with our human ear. And this LP is measured in decibels dB. Another important term in the acoustic analysis is the spectrum. So let's to understand the spectrum, let's have the left hand side. We have a random signal for 0.3 seconds, which we can think as a sound recorded by microphone at some arbitrary position. But by looking at this random signal, it's very hard to comprehend any meaningful, insightful engineering quantity. But if you apply the Fourier transform and convert the time domain pressure signal into frequency domain, here we can have some meaningful insights. Once we do the FFT and we convert from time domain to frequency domain, we can see the spectra associated with this random pressure signal. Here we can see at 150 hertz, we see the sound pressure levels are significant, which means the frequency associated with this random pressure signal for a time period of 0.3 seconds have a dominating frequency at 150 hertz and with the sound pressure levels at more than 160 dB. So you can just imagine like the Superman when he enters into the telephone booth and comes out as actual Superman, and that's something you can put it in analogy for time signal of the pressure to the frequency domain based the spectra. So that's, I mean, in frequency domain, the spectra is so powerful and give a lot of insights for our own understanding. And further, the spectrum is broadly classified into two types: narrowband and broadband. Narrowband is also called tonal noise, tonal band, and where the energy is concentrated at the specific frequency. On the left hand side, we see the energy is associated around 1,500 frequency with sound pressure levels around 120 dB. So here the whole energy is concentrated at 1,500 hertz frequency. And the typical examples are the vortex shading, blade passing, and cavity duct acoustic natural frequencies. On the other hand, the broadband, where the energy is on over a range of large frequency, and there are no distinct tones. On the right hand side, we can see the energy, the sound energy is distributed over a large range of frequencies. And examples are the sound generated by turbulence or combustion or thermoacoustics. And another important topic after looking at the types of the spectra is the frequency bands. And there are many types of bands, but here we see octave and third octave bands. These are quite often used in the noise legislations. And the resolution which we have seen in the previous slide is depend on the resolution is depend on the time signal, the time length of the length of this time signal which is taken. And oftentimes it is desirable to compare results of a different resolution. And in that case, converting the narrow band or broadband into bands that can help to normalize the energy content in the narrowband and broadband on the bands, and that will help us to take out the dependency on the resolution which is coming out of the time sampling length taken for calculating these spectra. Here we see the octave band. So each band have the energy of the narrow band has been integrated over one band, and at the end of each band, the frequency is double than the starting of starting of the each band. And in the third octave band, each octave band is divided equally into three parts. What causes noise, or in other words, what are the typical sources of sound? As we have seen in the definition of the classical definition of the acoustics, we have seen the vibrating surfaces as the source of sound, and pistons, loudspeakers comes under this category. And turbulent flow and structure interaction would be one kind of noise source. The typical examples is blade passing noise or rotor stator interaction. And sometimes the turbulence itself would become source of sound. The example is jet noise. And in the case of feedback, like the whistling and jet screech, there's a strong coupling between the flow part and the acoustic part through the feedback mechanism, and that would become one kind of noise source. And when there is unsteady heat release, sudden heat release, so that would also become a source for highly fluctuating pressure field as a result of highly high gradients of temperature field. Example is combustion, which is called thermoacoustic pro problems. Here we see the volume fluctuations as a source of sound. Uh, in this example, what we see here is a pulsating sphere sitting at the center of the domain, and because of its pulsation, it's creating the fluctuations in the pressure field inside the domain, and that would become as a source for the sound. Similarly, here the vibrating surfaces would become a source for sound. Here what we see is, instead of having a pulsating sphere, here the cylinder is moving back and forth from left to right and right to left, and that creating fluctuations in the pressure field of the domain, and that can be sensed as a source for the sound. The vortex sound, when vortexes impinge on a solid surfaces, they could become source for the sound. Here, one example would be leading edge and trailing edge noise, and also duct noise inside duct. If there is a rushing flow, and because of that, there's a flow separation, and there is because of the flow separation, we see a lot of vortices being generated, and when the generated vortices interact with the surfaces of downstream, then that would become an example for vortex sound. A cavity noise, we have seen this example in the previous slides. Here, highly unstable shear layer oscillating and interacting with the trailing edge of the cavity, and become a source for the sound, and then from there the sound will propagate into all directions. And there is a strong uh, feedback connection between the sound flow field and the sound field, which is produced and propagated. Leading edge noise. Here, what we see is there are two cylinders sitting next to each other, and the when the flow separates from the first cylinder and interact with the second cylinder, and as a result of that, we see increased levels in the noise because of the presence of the rear cylinder, and this comes under the example of leading edge noise. And similar to the leading edge noise, there is a trailing edge noise. Here in this example, we see an flow or an aerofoil, and we see small tiny structures on the upper side of the aerofoil, and these structures are generated as a result of the transition of the flow from laminar to turbulent by a mechanism called Tolbin-Schlichting waves. And as they propagate downstream and interact with the trailing edge, and that would become source for the sound, and the generated sound will propagate in all directions. So, so the sound source is at the trailing edge of this airfoil. In this case, it's an ACA 0018, a blunt airfoil. Sometimes the turbulence itself become the source for the noise. And in this case, there is no influence of boundaries. Here we see a jet which is coming out of some pipe, and then we see what we see is uh, because of the highly unstable shear layer, where we see vortexes are formed, and then they grow and deform and merge together, and again they break down into further small vortices. So all these kind of phenomena is because of the turbulence being generated in the flow. A cavitation noise is an example for the hydroacoustics problem. Here, in this case, we can see in the valve, the internal flow through the valve, downstream of the valve, we can see because of the low pressure, which goes below the vapor pressure of the liquid, working liquid, and then as a result of that, there is a generation of the vapor bubble, and they locally collapse and implode, creating locally highly unsteady pressure field, and that can be sensed as the sound, and which can propagate to in the vicinity of uh, the equipment and sensed as a sound and noise. Uh, the aeroacoustic modeling approaches in STAR-CCM Plus. In STAR-CCM Plus, the aeroacoustic analysis can be performed by two approaches. The first one is called direct noise calculation, and the second one is the hybrid method. And within the hybrid method, there is a integral method approach, and the other one is the computational method approach. Integral method approach evaluate the sound sources on the control surface. We will see what does it mean by the control surface, and it propagates the acoustic information to the far field using some analytical solutions. On the other side, computational methods solves an additional PDE called acoustic perturbation equation uh, uh, for the sound propagation using some specialized numerical methods. Direct noise calculations simulate both flow and acoustics using a single numerical method. And direct noise calculations are unsteady and compressible in nature, where uh, high fidelity models like detached eddy simulation, large eddy simulation are used. And it captures both sound and generation and propagation in a single simulation. And it can be used for scenarios where there is a strong two-way coupling between the flow and noise interactions. Examples include whistling, buffeting, a sunroof buffeting, or a side window buffeting. And in some special examples, like where sound wave induced vortex shedding. So sound propagation, the propagated sound can induce some motion in the components. That's where there is a strong coupling between the sound field and the flow field. The benefits of direct noise calculation is it requires a few modeling assumptions, and it involves less work to set up. And the typical challenges for the direct noise calculation is long computational times because of the need for smaller time steps. And it requires high numerical accuracy, meaning to say that it requires at least second order numerical scheme for time discretization and convection term. And it involves large mesh sizes, which means it requires a huge number of cells to to localize and characterize the sound sources, and also along with the high cell quality. Typical applications include if the measurement location is close to source, which means if the propagation to be predicted or solved is in the near field, and in the applications where the hybrid methods cannot be used. Example, the two-way coupled flow acoustic interaction, where the hybrid methods cannot be used. That's the limitation with the hybrid methods. In the hybrid method, it divides the simulation into multiple steps. The CFD is carried out for capturing the sound sources, and for the propagation of sound sources from the source to the observer location, additional equation is solved. Within the hybrid methods, in the integral methods, which are based on the FW-WCS William Hawkins model, it evaluates sound sources on the control surfaces, and it calculates the propagation of the acoustic information to the far field using some additional analytical equations. And further, within the integral methods, there are two approaches based on the type of the treatment required for the control surfaces, which is called impermeable FW-H and permeable FW-H. We will see in detail in the next slide. In the computational methods, an additional PDE is solved, which is called which is part of acoustic wave model implemented in STAR-CCM An, which solves for the sound propagation using specialized numerical methods, which is we have discussed in the previous slide. Yeah, so the model of impermeable FW-H evaluate the sound sources on the control surfaces. In this example, again, we have taken the flow NACA 0018 aerofoil as an example. Here, what we see is if we use this impermeable FW-H approach, the surface of the NACA aerofoil would be considered as the control surface, which is impermeable in nature, and the sound sources are evaluated by the surface integration on this boundary of the aerofoil to calculate the strength of the sources. And this model will not take the volume sources into account. And the typical use cases for this impermeable FW-H model is when the observer is in the far field. Here, the observer in this case of NACA 0018, which is outside of the computational domain, meaning to say that if we use this model, we don't need to include the observer into the computational domain. We can have a small domain to calculate the sound sources, and the observer can be outside of the computational domain. So that's the advantage of the integral methods compared to the direct noise calculation approach. And it is useful when the volume sources are not significant, and also when the sources are acoustically compact, meaning to say that the size of the sound sources are smaller than the wavelengths of the sound propagation. Typical applications include the fan noise and propeller noise, where in both cases the blades of rotating the components are modeled as impermeable FW surfaces or control surfaces, where the sound sources are evaluated by surface integration for the strengths of the sources. In the permeable FW approach, again, the sound sources are evaluated on the control surface, but the way the control surface has been defined is different compared to the impermeable FW approach, which you have seen in the previous slide. And this model assumes that all the sources are contained within the control surface. In this example, here we see, in the example of jet noise, we see the flow is coming out of the jet, the nozzle lip, and here we see the growing instability layer, and which is contained and confined by a control surface, which is an open cone placed around this growing instability, growing growing layers. And once we have calculated this sound sources on these control surfaces, and that information can be propagated to the desired observer location, which is far away from the sources. Uh, and this model is applicable to the cases where the volume sources are not negligible. In this case, this is jet noise is a case of a turbulent noise source where uh, the volume sources are important because the growing instability layer is a typical example for volumetric sources. Typical application is the jet noise. And the final approach within the STAR-CCM place for the aeroacoustic analysis, the acoustic wave model. Um, Here, it solves the incompressible CFD and solves acoustic wave model equation for propagation part. And the sources are calculated from the hydrodynamic pressure based on the acoustic perturbation equations. And the typical use cases for this model is when the observer is in the near field and the flows at a low Mach number of flows. Uh, because if the flow is at the high Mach number, the compressible effects are not negligible, and that's a limitation of this model, uh, which can only be applicable for the low Mach number flows where the compressible effects are not significant. And sometimes it is desirable to see the separation between the hydrodynamic part and acoustic part of the problem. Then this acoustic wave model approach is a suitable approach. Typical examples are side mirror noise. Here we see in this example uh, a side mirror sitting on the some surface, and we see at the top the flow field in terms of the pressure fluctuations around the side mirror, and using that hydrodynamic pressure information by solving the acoustic wave model, we can calculate the acoustic perturbation equation sound sources, and from the sound sources we can calculate for the acoustic pressure field around the side mirror. So so this is the typical approach within the using the acoustic wave model. The final topic is the methodology for Aero-Vibro-acoustics within using STAR-CCM plus. Here in this example, what we see here is a typical car with significant various noise sources. In the case of electrical vehicle, when there is no internal combustion engine, so the noise radiated by since there is no internal combustion engine, so other kinds of noise sources are significant. So they could be in the electric vehicle. In place of the IC engine, there's electric motor, so that create some sort of noise. And along with that, there are HVAC systems for the air conditioning of the cabin space, and in the HVAC ducts, we see we have seen previous slides that the rushing flow inside the internal rushing flow inside the ducts could become a source for the sound. And also we see side mirror noise uh, as a result of the separate turbulent flow which is separating from the side mirror and interacting with the surfaces of the car or vehicle. And also we see the wind noise, which is because of the aerodynamic loading on the side window. And also we see on the top when the turbulent boundary layer is interacting with the upper surface of or roof of the car, that could become one kind of sound source. So to demonstrate the methodology for aero-vibro-acoustics, we consider the HVAC noise as an example. And as I explained, uh, HVAC noise is caused by the oscillating pressure loads on the inner surface of the HVAC duct because of the highly turbulent flow, and that would result into a sound radiation into the cabin towards the driver and passengers. So the typical workflow for the aero-vibro-acoustic analysis for the HVAC duct noise as a source is as follows. So it starts with calculation of the turbulent flow field in the source regions. In this case, we have taken HVAC duct and a fan inside the HVAC as the sources, sound sources, and the turbulent flow is calculated using STAR-CCM An. Here we see the flow field on inside the HVAC duct and on the duct surfaces. So once we have a CFD result, we can use that output of the CFD result as input to the SimCenter 3D for some pre-processing, where within the SimCenter 3D, the CFD result can be converted as a load and sources for the aeroacoustic analysis within the SimCenter 3D. And once we have the loads and sources using the SimCenter Nastran solver, the acoustic field inside the cabin, car cabin, can be solved, predicted. So the calculated turbulent flow field in the source regions, which is HVAC duct and on the fan blades, can be exported as in a CGNS format at each and every time step, and this can be imported into the SimCenter 3D for some pre-processing, where the imported pressure are mapped to the same boundaries as pressure in the frequency domain. So the 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 output of the CFD calculation is typically the pressure field in terms of the time domain. And once you import, and then through the pre-processing, you can convert that time is to the pressure into the pressure in a frequency domain, and the surface pressures on the fan blades can be converted as the fan blade forces in time domain, and they can be visualized in SimCenter 3D. Here we see in the top on the top we see the pressure field in frequency domain, and in the bottom we see uh, the fan surface pressures are converted into loads which are in time domain on the surfaces of the fan blades. Once we have the loading and pressures in frequency domain within SimCenter 3D using the load recipe module, these loads can be easily connected to the solvers in the SimCenter Nastran platform. And then there is also need to convert or transform the pressure loads into the boundary conditions, which are in terms of the acoustic velocity, and also the blade forces as the rotating point sources. And once we have all the necessary boundary conditions and loading conditions, so within the SimCenter 3D, the cabin space can be generated. Cabin space can be meshed by finite elements, and using the FEMO, which is called finite element adaptive element order solver, the interior uh, the the radiated sound field from the noise sources, which are HVAC duct and the fan blade surfaces can be modeled, and we can see the sound pressure levels at different frequencies or the dominant frequencies, and that would result into uh, the animation which we see on the right side, extreme right side. Here in this animation, what we see is uh, the flow field which is calculated by the Sims International solver for acoustic field inside the car cabin by using the loading conditions and the CFD data which was converted into all the boundary conditions required for calculating uh, the sound field using finite element solver FEMO. So with that, the presentation concludes. And then the and then this acoustic response cases can be exported in a OP2 format, and then they can be used further in the processes or analysis in the downstream. Yeah, with that I conclude, and it's a time for question and answers. If you have any questions, you can use chat window, or you can send your questions and answers later on by using these mails. You can reach out with your questions by mail to support@vitalsplm.com or uh, or s12@vitalsplm.com. You can reach out by mail.